Right. So today's class will be on some other cryptanalytic techniques, or we shall be discussing about something more developed kind of attacks against block ciphers. Okay. So we have been discussing about block cipher cryptanalysis. We discussed about two major cryptanalytic techniques. One is called linear attacks and the other one is called differential cryptanalysis. Okay. So we will now see something which is more advanced and something which is more developed compared to them. Okay. And actually it's about, you have got a set of tools and you have to apply a tool to a given class of ciphers, right. So therefore you do not know the cipher will succumb against which kind of attack. So which means that you have to be knowledgeable about all possible techniques to cryptanalyze, and the moment you propose a block cipher, you have to certify that the block cipher actually passes through so many such number of tests. Okay. But these tests are not very strictly formulated, so therefore it will vary depending upon the properties of the cipher. So it is study the properties of the cipher and know how the attack works, and then you have to design or rather tailor the attack according to the given cipher. Okay. So it's so therefore that is the whole. So in today's class we will discuss about two major classes of attacks. One is called boomerang attack and the other one is called square attack. Now why have I chosen these two attacks? I will come to that very shortly. So, but before I go into these two attacks, this is an overview of some common cryptanalytic techniques. So you can see that there is a whole lot of repository. Okay. So we have been discussing about linear and differential cryptanalysis. So we also have differential linear cryptanalysis, and then there is something called impossible differential attacks. There is something called truncated differential attacks, higher order differential attacks, probabilistic higher order differential attacks. There is something which is called integral attacks. Okay. So then there is boomerang attack, rectangle attack, slide attack, interpolation attack, square attack, and we also have something which is called side channel or fault attack. So therefore these are not very conventional kind of cryptanalytic methods, but rather exploits the implementation weaknesses. Okay. So side channel attack falls into that class, and fault attacks are those, if in the cipher there is a sudden intrusion of, or rather either due to intentionally the fault is induced, or accidentally the fault can be induced, then you study the faulty cipher text and the fault free cipher text, and from there you try to deduce the key. Okay. So that now fault is also a very important issue nowadays, because the moment you are going into smaller and smaller technologies like nanoscales and things like that, faults become more obvious. Okay. So that amount of study is also done, and there is some class of attacks called correlation attacks or statistical attacks also. So this is actually something like you study various kind of properties. This is something which we have done previously also. We have seen in case of classical ciphers, we have been doing various kind of statistical techniques, right, evaluating various like the Kaspersky test, the mutual index coincidence test, all of them were essentially statistical tests, right. So there is something which is called correlation. So therefore it's very hard to draw a line between one attack and the other attack. So actually you can say the differential attacks and correlation attacks are vastly connected. Okay. Then there is a more advanced kind of attacks called algebraic attacks. So what it does is that it studies the Boolean functions of each of your ciphers and tries to see whether your Boolean functions can be exploited in some technique, can be solved essentially. Okay. So therefore you form an algebraic set of equations and try to solve those system of equations. Okay. And there was one quite a very significant progress in algebraic attacks, and lot of stream ciphers were shown to essentially succumb against algebraic attacks. Okay. And it was supposed to pose a threat against AES also at some point of time, but it has really not sustained, and AES is probably quite strong against algebraic attacks. Okay. So again, that is a debatable issue, but in today's class we will essentially discuss more about two classes of attacks. But why are we discussing about boomerang attacks? That is, first I will try to stress on that point. Okay. So we have been seeing in our previous discussions on differential attacks that our objective was to eliminate high probability differentials, right. So therefore the idea was that if we can eliminate high probability differentials, then we should guarantee security, right. So for example, we can show that if the upper bound of any possible differential is a p, right, that means all possible differentials are having a probability which is less than p. So then thumb rule is that if you try for say 1 by p number of texts, then you can break the cipher. Okay. So what does it mean? If I am able to, if I would like to increase the security, then I would try to reduce the value of P, right. So differential cryptanalysis gives us this sort of idea that if I am able to reduce the probability or probability P of any differential of the complete cipher, okay, or if the cipher has got R rounds, if I am able to reduce this probability for say R minus 1 rounds, that was the idea of differential attacks, then we should be able to guarantee more security, right. So we will see actually this Fock theorem is wrong, okay. So therefore there are two classes of attacks which exploits the incorrectness of these assumptions, okay. One is called impossible differential attacks. Although we will not be discussing on this attack, it mainly shows that if there is a differential whose probability is actually sufficiently low, then also you can exploit that for an attack. So therefore it says that if you can show that certain probability, certain differentials will never occur, then also you can use that as a pruning methodology, okay. So therefore you can again guess the key and you can see that whether a particular differential holds or not, okay. So in that case it's just the opposite of a differential attack kind of, okay. Therefore certain differentials can never occur, that's the idea. But the boomerang attack is more interesting because what it says is that even if no differentials for the whole cipher has got either high or low probability, okay, then also you can break the cipher using a differential style technique, okay. So that is more alarming. So therefore it shows that actually although your total cipher or complete cipher is quite secured in the sense of differential attacks, that means it, and even in the sense of impossible differential attacks, because that means that it has got neither a high differential nor a very low differential, but even then you can try to mount a differential kind of attack to break the system, right. So therefore we will be discussing about this attack which is called the boomerang attack. So therefore the boomerang attack basics are essentially upon, I mean in case of differential we were considering two such plain texts, but in this case we will consider 4 plain texts, okay. So we will be considering P, P dash, Q and Q dash, and we will say that P, P dash, Q and Q dash form something which is called a quartet, okay. So the attacker, what it does is that he essentially chooses first of all P and P dash and does a decryption, okay, and then what he does is that he obtains Q and Q dash by decrypting the corresponding by decrypting 2 corresponding cipher texts, okay. So therefore the idea is as follows. So what you do is that you take P and P dash, so these are essentially 2 plain texts, and then what you do is that you apply the encryption function, and I denote that by E, okay, and then you obtain 2 cipher text, right. So you obtain say for example C and C star or C and C dash, okay. Now from here you do certain thing and arrive at another 2 cipher texts, and I call them D and D dash, okay, and then you decrypt D by E inverse, that is a decryption function, and you also decrypt D dash, and you obtained 2 plain texts and I call them Q and Q dash, okay. So here this P, P dash and Q dash form something which I call as a quartet, okay.
What key are they using for encryption?
That I don't know.
How will we obtain the quartet if you don't have the key?
So you know that we have been discussing about various models of attacks. So there are some model of attacks which are called like chosen plain text attacks, known plain text attacks. So in those cases, what do we assume? That we can essentially encrypt or decrypt even if I don't know the key. And if you remember that I have given you certain practical scenarios where that is possible as well, okay. So these are various models of attack, like so in linear attacks and differential attacks also we have assumed that we know the plain text and cipher texts. How? Because that belongs to a certain model like known plain text attack or a chosen plain text attack, okay. So therefore in this case it's also an example of chosen plain text cipher text attack, because in this case you are not only choosing the plain text but you are choosing the cipher text also, right. So therefore this P, P dash, Q and Q dash forms something which I called as a quartet, okay. So therefore, so now coming back to your slide, you see that there are 4 queries that you have done. So therefore you are doing 2 encryption queries for P and P dash, and you are doing 2 decryption queries for D and D dash. So therefore, how many queries you are doing? You are doing 4 queries, right? So therefore, now you can actually, so we have in our diagram we have seen that we had the cipher E, right? So what we can do is that we can think that this E is composed of 2 smaller ciphers. Okay, so I call them, one of them as E0 and the other one as E1. So E0 is the first half of the cipher and E1 is the second half of the cipher. So half does not means the exactly half. Okay, half just means portion, the first portion and the second portion. Okay, so what you do is that you do a differential characteristics for the half ciphers. So what you say, you take E0 and you give that. So therefore, what you do is that you obtain differential characteristics for half of the ciphers. So even if you are not able to obtain good differential characteristics for the entire cipher, suppose you are able to obtain differential characteristics for half the cipher. Okay, so what you do is that you obtain characteristics for E0, you obtain a characteristics for E1 inverse. So the characteristic for E0 is denoted by this particular characteristic, that is, you give delta and you obtain delta star, and for E1 inverse you give lambda and you obtain lambda star. Okay, so these are your individual half characteristics for half the cipher that you have done again by observation. Okay, and suppose that these particular characteristics has got reasonably high probability. Okay, although you do not have good differential characteristics for the total cipher, but you have reasonably high probability for the half ciphers. Okay, is this till this portion clear? So what you do after this is that you start observing something like this. So therefore, now the same diagram you can observe by splitting up E into 2 parts, E0 and E1, and also for that for the entire quartet. Okay, so now you come to this diagram. I mean, I will show you with. So what you do is this. So now the same diagram, what you do is that you see that P and P dash, and you observe by breaking up the cipher E into 2 components. One of them is E0 and the second component is E1. Okay, and you obtain the corresponding cipher. That corresponding cipher is denoted by C. The same thing you have done for P dash also. So P dash also, as you operate E0 and you operate E1 and you obtain C dash. So now you assume that this P and P dash maintains a constant differential delta. Okay, so in that case, if I assume that E0 passes a differential, say delta to delta star, so that means that at this point we have a differential, expected differential of say delta star, right? So now what you do is that you have obtained C and C dash, you apply an XOR function, you take the cipher text and you apply an XOR function of say lambda, and you obtain 2 ciphers texts called D and D dash. Okay, and then what you do is that you start the opposite operation, that is, you start the decryption. So you take this and you apply the decryption function, which means you apply E1 inverse and also apply E0 inverse. Same thing you do for this also. You apply E1 inverse, you apply and obtain E0 inverse, and then you obtain, what do you obtain here? Q and Q dash. So now you see that for E1 inverse, okay, you have basically given a differential of lambda, and so therefore what you would have expected here is that the differential here is lambda star, and same for here also. So in that case, what is the corresponding differential existing at this point between these two things? What is the corresponding differential? It is the same as delta star, right? So therefore you obtain delta star here also. So now, since we know that delta gives delta star, by symmetry we know that delta star will also give delta, right? So what you obtain back is that you are expecting here a differential of delta again. right. So it's something like a boomerang. So you see that you are throwing a differential of delta and you are expecting back a differential of delta, okay. So the idea is, you know, that similar to what you like a boomerang, right. So therefore you throw something and you obtain back something, okay. So therefore this is the entire basic principle behind the operation of boomerang attacks. So you see that this same thing is being denoted here by some equations, but what is the idea is that at this point, like E0q and E0q dash, I am expecting here a differential of delta star, because if I know that here the differential is delta star, I've discussed why it's delta star, then it implies that here I am expecting a differential of delta. So note that this characteristic is the same as the inverse of E0, okay. So therefore it's the same as that of, so therefore this we have discussed already, that I mean, if you have a characteristic for E0, we have a similar characteristic for E0 inverse also, okay. So thus the difference in the plain text Q and Q dash is the same as that in P and P dash, and hence the name boomerang. So therefore you are throwing a differential and you are obtaining back the differential, right, you are getting back the differential. So we will study one cipher to understand how the boomerang attack works, okay. The name of the cipher is called Coconut 98 and it was given by S. Vaudenet, and I will just give the reference for this particular work, and it was given with the idea that they essentially gave a theory which will always protect against differential cryptanalysis, okay. So it was a very nice theory, it was known as the decorrelation theory, and using a decorrelation theory they proved that actually you cannot obtain any good differential characteristic for the entire cipher, okay. But then people again tried, I mean found out this boomerang attack and showed that although you are not able to do a differential cryptanalysis, but you can still do an attack, okay, because half of the cipher was not so strong. The full cipher was quite strong, but the half of the cipher was not really strong, okay. So this attack was given by a prof from UC Berkeley. His name is David Wagner. So I will give a reference for that also. If you are interested, you can download and study that paper also, okay. So therefore what is the idea? The idea is that we are essentially using a 256-bit key in this Coconut cipher, and this is essentially a 64-bit block cipher. It's something like a Feistel cipher which we have studied, okay. So this is a, roughly speaking, it's not so important for us, but just observe that there are, so the idea of a Coconut 98 cipher was that it had 3 components, okay. So it had 2 Feistel layers and in between there was an M layer. I call it an M layer, actually it's a decorrelation layer, but for our simplicity let's call it an M layer, okay. So you know that if there are 4 rounds, for each Feistel layer there are 4 rounds, okay. So therefore there are 4 rounds at the beginning and 4 rounds at the end. So how many keys do I require? Round keys, I require 8 round keys, okay. So this is a very simple key shielding algorithm which says how you are generating those 8 round keys, okay. You take K1, so therefore the 256-bit key you can decompose into 8 components, each of them of size 32 bits, right. So therefore you take K1 of 32 bits, and that gives you your first round key. For second round key you can just XOR that with K3 and you can obtain the second round key. For the third round key you XOR that with K4 and you obtain this, and for the fourth round key you XOR this with K3. So you see you are XORing with K3 alternatively, K3 and K4 alternatively, right. So therefore you can actually implement this quite easily in hardware or any other implementation. So you take K2, you XOR this with K3, you take K2 XOR K3, XOR that with K4, and again you take K2 XOR K3 XOR K4, you XOR that with K3, you obtain the 8th round key, okay. It's a very simple technique to generate all the round keys. So this is how the Coconut cipher looks like. The details in this case I will again elaborate, but broadly this means looks like this. It's a 64-bit block cipher. So that means that these 2 components are each of 32 bits, right. And you see that this network is just like a Feistel cipher. It looks like DES, right. So therefore there are 3 parts. There is an M layer between 4 Feistel rounds. So there are 4 Feistel rounds here, 4 Feistel rounds at the end. In between there is a layer which we call as the M layer, okay. So let's look into the Feistel rounds. The Feistel round just remembers us of DES. So you see that there are 2 parts, left and a right part. You take the right part and bring it to the left, so that forms your left part, and in order to obtain the right part you take Y and pass that through a function, XOR that with X and obtain the corresponding output, Okay. So here you see that you have first of all done a round key, and after that you have done certain sequence of operations. Okay, and that is something which is a constant C also. So what is the operation size here? The operation size is 32 bits, right? So therefore, because this part is only of 32 bits. Okay. So you see that there are some components here. One is called phi, one is called roll 11, and then there is an integer addition, and then there is again an application of the function phi. Okay. So what is roll 11? So roll 11 means you are doing an 11-bit circular shift to the left. Okay. So it just means that you take this value, and I mean the entire output, and you just do a circular shift to the left by 11 bits, 11 steps. Okay. So let's see what is the function phi. The phi function is this, that is you take x. So what is the size of x? 32 bits, right? So you do an x mod 256. What does it mean again? X mod 256 means what? You are taking only 8 bits, right? So you are taking only 8 bits, and you are basically neglecting the other part. Okay, and that you are passing through an S box which actually takes 8 bits and produces a 24-bit output. So this is an example of an expansion S box. Okay, you take this S box and you obtain 24 bits here, and then you multiply that with a constant called 256, and then that you add by an integer addition with x. So what is the size of x? 32 bits. You add this and you do a modulo 2 power 32 addition, and you obtain the corresponding output, right? So this is the basic idea behind the function phi. Right? Is this clear? So then what we do is that we see what is the M layer. So the M layer is as follows. You take xy. So what is the size of xy? 64 bits. Then you use the components k5, k6, k7 and k8 of the key, and what you do is that you take xy, XOR that with k5, k6 and multiply that with k7, k8. Note that this multiplication is in the Galois field 2 power 64. Okay, and this is the reduction polynomial which they have used. Anyway, so these are just details. Okay, so this M layer is actually designed, is based on something which we call as a decorrelation theory, and the idea is as follows, that you see one object particular, or you can, if you do a differential analysis of this layer, then what do you observe? If you do a differential analysis of this particular layer, then k5, k6 gets cancelled. You see that? Because you are doing an XOR here. Okay, all of us see that? So you take xy and you also take another x dash y dash, and you know that is x dash y dash XOR with k5, k6 multiplied with k7, k8, and you take an XOR between them. What you get is this particular k5, k6 cancels with the other k5, k6, and so what you obtain is a differential, but the differential is multiplied with k7, k8, right? So therefore what does it mean is that if k7 and k8 are unknown, then the probability that a non-zero input differential will produce an output differential is actually 1 by 2 power 64 minus 1, because if I keep on changing the values of k7, k8, and how many choices of k7, k8 are there? There are 2 power 64 choices. Okay, and I know that the 0 value can never occur, so that excludes that 0 value. So there are totally 2 power 64 minus 1 non-zero differentials that are expected. Okay, and out of them I am interested in only one case, so the probability is 1 by 2 power 64 minus 1 if the value of k7 and k8 are unknown. But if the value of k7 and k8 are known, then automatically the differential gets fixed, right? So but for a fixed key, the output differential does not depend on the input value, that is the main idea, but it depends only on the input differential, right? So if I fix the key, the output differential actually does not depend upon the input value, but it depends only on the input differential, right? And if I do not know the value of k7, k8, then it's very hard to predict a differential. All the differential have got uniform probability. So therefore you see where is the problem if I do a normal standard differential attack here, analysis here. So you see that I have got this mxy, this is equal to xy XORed with k5, k6 and multiplied with k7, k8, forget the modulo at this point. So I take again mx dash y dash, okay, I call that xy dash, okay, that's a some other text basically. So what you do is that you take xy, so I call that xy dash, you XOR that with k5 k6 and multiply that with k7 k8, right. So this is the other pair. So now if we do a differential of these two things, then what is the expected differential at the output? This will depend upon xy XORed with xy dash, but this differential is multiplied with k7 k8. So that means that if I am doing a differential analysis, then what I am trying to do is that I am trying to force a differential at the input of your m layer. So I call that an m layer. Okay, I am trying to force a differential here, and I am trying to compute what is the probability distribution of the differentials here. Okay, so here you see that if I do not know the value of this corresponding key called k7 and k8, then I do not have any preference of any key. I mean, for every key, okay, for every key you essentially you see that if I change this value, then automatically if I change this delta here, then I get a different delta here. I change this k7 k8 to another value, I obtain another delta, right. So therefore if I do a similar kind of differential distribution table, then I will see that the probabilities are quite uniform. Okay, for every key you will get that, I mean for every choice of key the probability is 1 by 264 minus 1, because the 0 differential will not occur. Okay, that is the idea, right. So what you see is that in this, using this particular technique, the designers were able to impose a uniform distribution among the differentials. Okay, so therefore doing a standard differential attack at this point is quite hard because of this, because now you have been able to develop a technique through which you can have a uniform distribution of the differentials. Okay, so that is the basic idea of the decorrelation theory. Okay, so now we will do a differential analysis of the phi function also. So what it says is that you suppose you know that this is your how the phi function was looking like. So let's do one thing, let's subject it to a certain differential. Okay, so we take Ej. So what is Ej? Now Ej is an input differential in which so it's a 32-bit differential in which the jth bit is flipped. Okay, so you flip only one particular bit. So you see that if your j varies from 8 to 31, then what is the differential here? It's actually 0, because here you are taking only the last 8 bits and I have not varied those bits, right. So therefore here you are obtaining the same input. Okay, so therefore in the S box also doesn't computes on the same values, and it really doesn't matter what it goes inside. Okay, but what about this part? You see that Ej is transferred here. So now you see that you are basically doing an integer modulo 2 power 32 addition, where one of the components is flipped by 1 bit, right, and the other part is held fixed. Okay, so then the probability that in the output you will find that the jth bit is flipped is actually half. Why? Now because it depends upon whether your carry in bit at that point is 1 or 0, right, because here you are doing an integer addition. So integer addition means that there is an input carry also, right. So if your input carry is 0, then automatically it means that the jth bit of the output is also flipped, right. So therefore if you do a little bit of analysis, we will see that this probability, if you study the carry bits, is actually close to half. Okay, for this class just assume this fact. Okay, yeah.
Where is this carry coming from?
Yeah, we are doing an integer addition here, na? Normal addition. So you are taking this and you are taking this. So this is a normal integer addition. Okay, so although I am saying at this point the differential is 0, but the actual value is not 0. You are processing on 2 inputs. But the idea is that for both the cases, that is for both the differential pairs, you are essentially processing on the same input at this point. But what you are varying is only this part of the input. Okay, here only the jth bit is flipped. And what is the probability that in the output also the jth bit is flipped? That depends upon your carry, how you are able to control the carry bits. Okay, and you can actually show that the probability is very much close to half. Okay, so at this point, so actually the carry bits follow a very neat probability distribution. So that is, I mean, not a objective of our class. Okay, but we can actually see that this you can actually prove theoretically that what is the probability that a particular carry bit will be 0 and when it is obviously when it is 1. Okay, it is actually half plus half to the power of I plus 1, where I is your bit location. Okay, but that is we can actually theoretically prove that also. So anyway, that is not important. So what is important is that you are able to get a differential in the phi layer with a probability of half. Okay. So the ROL 11 was a circular shift by 11 bits, right? So therefore what it will do is that it will take the EJ input, okay, and you see that here what you have obtained is, if you have given an input differential here of EJ, you are able to obtain an input differential here of also of EJ with a probability of half, right? But what are the subsequent operations here? The subsequent operations are that after a phi layer you are doing an roll 11, okay, and then again doing an integer addition and again followed by a phi function. So you see that in this phi function there is one integer addition, then in this C, when you are adding with C, there is one integer addition, and when you are doing this phi function there is another integer addition, right? So therefore now what is the probability that so if I do an EJ here, I should be able to obtain an EJ here also, and the probability of that is half that we have seen. Okay, so therefore due to this rotate 11, this J bit gets shifted to J plus 11th location, right? It gets shifted to the left. But what about this plus function? If I would still like to maintain the differential at the J plus 11th location, then also I need to control these carry bits, right? And similarly also for the phi function. But here, so therefore we may think that what we have obtained for one integer addition, we may have to multiply that probability for the 3 successive integer additions, right? But actually it's not so, because these 3 integer additions I can squeeze them and write as one single integer addition, right? So therefore the idea is because of this property that you know that if I do x plus a mod 2 power 32 and then add b mod 232, this I can write as x plus c mod 2 power 32, right? So which means although we have to control 3 integer carries, 3 integer additions, we actually can squeeze them into one single integer addition. Okay, so therefore the probability that this input differential of EJ will actually yield an input output differential of EJ plus 11 is actually close to half, okay, and not half into half into half. Okay, so similarly you can obtain other such kind of differentials also. So for example, you take EJ and you XOR that with EK, the probability that this will yield EJ plus 11 XOR EK plus 11 is actually 1 by 4. Why? Now because you take half and you take another half, so you multiply them because they are independent, so you get 1 by 4. Okay, so assume them to be independent another. Okay, so we will study one good characteristics propagation for these 4 rounds. Okay, so it's quite interesting. You see that suppose I subject this Feistel network to E19 and I subject this part to E18 XORed with E8. Okay, so what is the corresponding because of the Feistel network, this gets transferred here, so you obtain E18 XORed with E8 here. Okay, and this E19, so therefore what is the expected differential of the corresponding Feistel function here? So you see that what we have studied is that if I take EJ XORed with EK, it gets transformed to EJ plus 11 XORed with EK plus 11, right? So here we take E18 and E8 and add 11 to this index and add 11 to this index also. Okay, and remember that when we are doing this addition on the integer on the indices, then we are doing a mod 32. Okay, so what is 18 plus 11? 29. So you obtain 29 here, and what is 8? A plus 11, it's 19. So now you obtain a differential here which is equal to E29 XORed with E9, right? So if I take an XOR between these two, you see that E19 gets cancelled, right? So you have only E28. So this, or rather E29. So this E29 now gets to the right side, right? And you obtain E18 XORed E8 here. So what is the expected differential now at this point? It is E29 plus 11. So what is 29 plus 11? 40. So you take mod 32, it's 8. So therefore E8 gets cancelled and you have only E18. So you see E18 comes to the right. Okay, and to the left, what comes? E29 comes. So if you take E89 here, then add 11 to 18, what do you get? You get 29. So that cancels this one. Okay, so actually you should get 0 here. Okay, so I have written this as wrong actually. This will be E0. Okay, so this is 0, and you obtain here E18. So therefore, you see that if you throw a differential of E19 and E18 XOR E8, then the probability that you will get here E18 and 0 is actually equal to half, approximately equal to half into half into half into half. Okay, so that means it is equal to 2 power minus 4. So this is a standard differential analysis. Okay, so therefore, if I obtain a differential in this nature, by similar symmetry, we can also do the same thing for the backward thing also. Like if I throw E18 and E0 here, or rather E18 and 0 here, then I should obtain back E19 and E18 XOR E9 or E8 with a probability also of 2 power minus 4, close to 2 power minus 4, right. So therefore, I obtain a differential for the forward transformation, I also obtain a differential for the inverse transformation, okay, right. So now what is my setting? The setting is that I have obtained a differential for the half of the cipher, one part of the cipher, and similarly I try to obtain a differential for the other, we have obtained for the other half of the cipher also, okay. So now you see that you can relate it to the boomerang attack. What you can do is that you can call this as E0 and you can call this part as E1, okay. So you take or include the M layer into the E1 cipher, right. So what you can do is that you can write this in this form, like you can take the cipher E and assume that it is composed of psi1, M and psi0, okay. So psi0 is the first part and the other part is psi1 and M. So therefore, first you apply an M layer and then a psi1. So what is psi1 and psi0? They are the fistal layers, okay. So you can basically break your cipher into two component ciphers, okay. So now you obtain, in order to obtain the full round characteristics, you see that you need to find some way to take advantage of these half round characteristics, okay. So you have obtained some half round characteristics and I would like to obtain find out some way through which I can take advantage of these half round characteristics, okay. So the M layer creates problem for standard DC, we have discussed why, right. So the boomerang attack helps us to control the effect of the M layer. So what it does, the key idea is this, that since M is affine, so if I fix the value of the key and if you throw an input differential, then the output differential is actually expected with a probability of 1, right. So that is the basic idea. So therefore, if I throw in a differential of lambda star, then your M inverse, so that is the inverse of your decorrelation or the M box or the M layer, then you are expecting a differential of M inverse of lambda star, right. So what is the idea? Therefore, what is the probability of this? The probability of this 1 if the key is fixed, okay. And the central idea behind boomerang attacks is that I am not really interested in the value of M inverse lambda star. In differential attacks, we were interested in the value of the differential at the output of the r minus 1th round, right. But in a boomerang attack, I am not interested in the value of that differential. What I am interested in is in the fact that this particular differential M inverse lambda star exists. That is, there is a particular differential for which this actually holds, okay. So coming back to this diagram, I mean you can see this, that is when we had thrown this differential here, that is delta here, I was not really bothered about what is the value of this delta star. What was important to us was the fact that actually you had some delta star. I am not really bothered about the value of the delta star, okay. So then what I do is that I take so I obtain this and I apply some lambda here and some lambda here. I am again not bothered in the value of this lambda star. What I am bothered is that both the ciphers end up in having the same differential, okay. Then again this property holds that I give delta and I get back delta as a differential. That is what I am more interested in. I am not really bothered in the values of the internal differentials, okay. So that is the key, that is another fundamental difference between the idea of boomerang attacks and normal differential attacks, okay. So in that case, I am not really bothered about whether I throw in a differential of lambda and I obtain back a differential of M inverse lambda and what is the value of that M inverse lambda. I know that there is an M inverse lambda which exists, okay. So therefore, what does it mean? It means that it does not matter that M inverse lambda star is unknown to the attacker. What is important is that it depends on the differential and not on the cipher text values, okay. So you define these two probabilities, that is the first probability is that on the psi 0 layer, that is on the first part, you have a probability and I designate that as if you throw in delta, you get back some delta star. So I denote that by some p delta star, okay. And similarly for the inverse transformation, you throw in lambda and you get back lambda star. So there is the inverse Feistel ciphers notation, and I denote that probability by say q lambda star, okay. So in this case you can see that your success probability is actually square of this and square of this and a sigma over this. Why? Now because there are two differentials of this nature and there are two differentials of this nature, okay. So and I am really not bothered in the value of delta star or in the value of lambda star. So I take a sigma over these two things, okay. And you can see that this, I mean this was worked out for an example delta lambda of equal to E10 E31, and it was found out that this probability was around 1 by 1900. So this is some empirical value. You do an analysis and you found out. So and you can do a similar kind of analysis like we have seen for our half differentials, okay. So now you see that what you have done is that you have thrown in a differential of E10 E31 and you are expecting back that this differential should come back to your q and q dash, right. So if I do not expect anything for this E10, then what is the probability? If I just guess only on the half of the stuff, then what is my probability? My probability doubles, right. My probability becomes equal to 1 by 950, okay. So therefore now we should be able to understand the actual attack. So therefore the actual attack works like this. So what it does is that it expects that, okay, so you throw in a differential of, as I told you, so you throw in a differential on p and p dash of this value, that is E10 and E31, and you expect back, because of the boomerang effect, you should get back q XORed with q dash, and that should be equal to, that should be also be equal to E10 and E31, right. But let us not assume anything on the first part, let us just assume on the second part. Why? Because the probability of that actually increases, right. I will have more number of cases which satisfies this fact. So my probability is around 1 by 950. So you note that therefore how many queries you are doing for one boomerang effort? You are doing actually 4 queries, right. So therefore if you do inverse of this, that is 950, if you obtain 950 quartets, then for obtaining those quartets you have to do 4 encryption or decryption queries, right, 4 chosen plain text or ciphertext queries. So in total you do 950 into 4, that is around 3800 chosen plain text or ciphertext queries, okay. And this should give you one useful quartet, that is the idea, okay. So this follows from the fact that if there is an experiment whose probability is p, then we can actually prove that you repeat that experiment for say 1 by p number of times, then you obtain a success. You can actually prove this fact, okay. So therefore what it means that if there is an experiment whose probability is p, and if you keep on repeating that experiment for say 1 by p number of times, then you should get at least one success, okay. The expected number of trials to get one success is actually 1 by p. So therefore here if I do say if my probability is 1 by 950, I should repeat this for how many times? 950 times, okay. And in each of those trials there are actually 4 queries. So in total there are 950 into 4 queries, okay. So and if I do so many queries, I should get one useful quartet. Useful quartet means what? I get back the desired differential for q and q dash, okay. It satisfies this relation. That is my success of my experiment, okay. So thus with around 16 into, so if I repeat this, I will this is just the empirical value. If I repeat this for say 16 into 3, I will explain why 16. But if I repeat this experiment for say 16 into 3800 queries, then you should get back 16 useful quartets, right, because you have obtained, through this you have obtained one useful quartet. If you repeat this for say 16 times, you will obtain again 16 such quartets, right. So 16 useful quartets are expected, okay. And why 16? Why 16? Any idea why 16? So this should become clear if we observe that what I am trying to obtain. First let us try to obtain the K1 key, okay. So what you do is this, that is you take one useful quartet, concentrate on one useful quartet, okay, and you guess the value of K1, right. So we have the fact that if P dash Q dash forms a useful quartet, then after one round of encryption, the XOR difference must be E31, 0. So that you can see, I mean, again using the similar techniques as I have told you, doing that plus 11, you can actually prove that this will be equal to E31, 0 for both P dash pairs and Q dash pairs. Okay. So maybe you can observe if you study this, that is what you are doing here is that you are taking a differential of E10 and E31, right. So if you take E10 and E31 here, and if you apply E10 and E31 here, you apply E10 and E31 here. So what do you expect here? 31 plus 11. So if you take mod 32, how much did you get? You get back 10. So E10 cancels with E10. So you obtain here a 0, and this particular E31 comes to the left, right. So you are expecting after one round E31, 0, right, if it is a useful quartet, right. So therefore that's what is written here particularly, you are expecting after one round E31, 0 for both P dash, and similarly you can show it for Q dash pair as well. Okay. So for the wrong keys, actually half of the times this will hold and half of the times it will not hold. Okay. So what does it mean? I mean, but for the actual key, large number of cases you will find that this is actually, I mean, it will always get satisfied for the actual key, right. So what does it mean? That you have got some event with a probability of half, which means what? That is, the information is of equivalent to 1 bit, right. I am trying to estimate how many trials I require. Okay. So you see that if I tell you that there is a particular coin tossing experiment, and you know the probability that for an unbiased coin, the probability of head is half. So what does it mean? The fact that head falls carries 1 bit of information, right. So now what I am saying is that for a random key guess, you have got half probability that this particular event will hold and not hold, right. So the fact that you are able to obtain, rather I tell you that this particular thing holds, carries a half probability, so that means it carries 1 bit of information. So therefore you should be able to get 1 bit of K1 through this information. Okay. So that means how many keys do you have? So therefore now you have got P dash, Q dash, each of them reveals 1 bit of information, equivalent to 1 bit of information, so that is 2 bit of information. And how many bits are there in K1? There are 32 bits. So therefore how many trials do you require to do? You require to do 16 trials, right. So therefore if you do 16 trials, you should be able to obtain the entire 32 bit keys. So this is a statistical idea, statistical guess. Okay. So therefore the idea is that if you do 16 useful quartets, you should be able to obtain the entire key K1. Okay. So that's the idea. So similarly you can obtain the entire key, that is the entire 128 bit key, and the complexity of this attack, I mean we cannot go into, let's not go into the details, but this is the idea, and let's try to at least understand that why boomerang attack works whereas normal differential attacks fail. Okay. So the complexity of this attack was around 2 power 16, because you were guessing the 16, I mean you are guessing the K1, so it's actually not 2 power 16, it's actually 2 power 32, because you are guessing K1, right. So and what is the size of K1? Oh, what is the size of K1? 32, right. So therefore this should be actually 2 power 32. Okay. So I'll just conclude then our talk with another kind of interesting property. I mean, we can actually study this by a very, so we'll again come back to AES. So we have talked about fishtail ciphers, and we will again just conclude with AES. So what was the idea of AES? So let's try to see how a disturbance works in AES. Okay. So I think I've already told you once in a class, that is, let us disturb one particular byte of AES. Okay. So if I disturb one byte of AES, okay, so how many such ciphertexts can I obtain? 256 ciphers. And I mean, how many such plaintexts can I obtain? 256 plaintexts, right. So therefore if I call this as an sort of, so therefore I can keep on disturbing these bytes, and I can obtain, say, P1 to P256 corresponding values of plaintexts, right. So I call this set as something which I called as an active set. Okay. So I call this as an active set. Okay. So these are various various inputs that you have taken. Okay. So therefore, coming back to the definition, you see that let this be an active set of 256 states that are all different in some of the state bytes and are all equal in the other state bytes. Okay. So I call such kind of sets as active sets. It means that in certain byte locations are active and certain byte locations are not active. Okay. So active means for all of them you are essentially they are different, but for the other locations they are same. So again, like in our diagram we have seen that for these locations, all of these things have got the same values, but these values are all distinct. So all of them are distinct values. Okay. So what is the property of this active set? If you add them, you get 0. You get 0 because these are all same. But what about this? This takes all possible values. So if you add them, then you will get back 0. So you can see that this property in AES remains invariant till 3 rounds. Okay. So I mean, if I impose or rather give plain text of this nature, then this property does not get disturbed for 3 rounds of AES. Okay. So that is the basic idea behind an attack which was called as square attacks. Okay. So you have an invariant that if you add them you get 0. Okay. That does not change for 3 rounds of AES. So if you take XOR of these things, you should get 0 for all possible values of I and j. So that is the basic idea which doesn't change. So therefore you see that let us see the invariance. Why the invariance? I mean, it is quite easy actually. So what you can do is that you can consider this set in which only one byte is active, and then what you do is that you observe the propagation of the active set through 3 AES rounds. Okay. So what is the first layer? The first layer is sub byte. So what do you do in a sub byte? You take you are basically considering a 1-to-1 map, right? So therefore, so if you observe the sub byte, you take one particular byte value here, and all of these values are distinct, right? All these values are distinct. So therefore, if you do a sub byte operation after this, right, or an add round key operation here, then essentially you will find a 1-to-1 map for every byte location, right? So therefore, in the output of this also you will get all possible values. So the property does not change because of the sub byte or the add round key. Okay. What about the shift row? The shift row will just transpose this; it will not change, right? So what about the what about the mixed column? So you see that in a mixed column, okay, if in one particular column there is one disturbed byte, then at the output of the mixed column all the 4 bytes gets disturbed, right? So therefore, in the you again obtain an active set, but only thing is that the disturbed byte propagates to all the 4 rows of one particular column. Okay. So that's the idea. So therefore, now if you see this, you see that the column in which there is so therefore this is why the justification why it doesn't change. Okay, why it remains an invariance. Okay. So let's start. I mean, for the second round add round key and the sub bytes also does not alter the property of 4 active bytes. In the second round, the shift row transposes 1 active byte to each column, and the mixed column converts each column to have 4 active bytes. Okay. So this is, if you have solved that example of diffusion which I told you to study for AES, this should become quite obvious. Okay. So what about the third round key? So therefore you will see that till the third round you essentially have the same property which holds, but now you essentially have the entire state matrix which is disturbed, right? So therefore all the ij locations are active now. So therefore now, I mean, predicting beyond this, that is the third round mixed column becomes hard, right? So that is little bit tricky, but you will see that this also follows if you observe the matrix of mixed column. Okay. So this you can see that, I mean, the property, although it doesn't remain an active set, but still the property that if you sum them you get 0 still holds. Okay. So that means that what you are doing is that XORing of mixed column aij, and remember that mixed column was a linear transformation, right? So therefore you can now bring out this in this fashion, and you can show that actually, so these are all XOR. So this is not 0 2 XORed with aij, it means 0 2 multiplied with the XOR of all aij's. Okay. So maybe I could have written the bracket here than written here there. Okay. So similarly for this also. So this is 0 3 multiplied with the XOR of ai plus 1j. Okay. And here also this symbol. So therefore if you XOR them, you get back 0. Okay. So therefore this property does, I mean, or if you add all the byte locations, the fact that you get back 0 doesn't change because of the third round mixed column also. Okay. but the sub byte will change it actually. And you know that in the last round, so if you consider a 4 round AES for example, then you know in the last round there is no mixed column, right. So let us consider a very smaller version of or smaller variant of AES where the last round does not have a mixed column. So what you do is that you just guess the key, you go back to the sub byte layer, okay, and you check whether the input of the sub byte layer, if you add all of them, then you get 0 for, then whether you get 0 for all the ij locations, okay. And if it's a correct key, then this should hold. If it's a wrong key, it should not hold. And the probability of this fact is 1 by 256. So again, you know that if you repeat this for 256 number of trials, you should be able to identify the key, okay. So that's the basic idea behind this attack, but you can just ponder upon certain points, that is, so what we have discussed is basically a square attack on 4 rounds of AES. So what you can just think is whether the square attack will work for 5 rounds, will it work for 6 rounds of AES, and will the same attack work for AES 192 or an AES 256, okay. So you can just think of on these problems, okay. So for the references that I have followed is Provable Security for Block Ciphers by S. Bourdonnais. So these are all freely downloadable, you can download them. The Boomerang Attack by FSC, was published in FSC 99 by David Wagner, and although this book is not really available, you can follow this particular work, the Block Cipher Square, okay. So this was written by Damon, Knudsen and Ryman. So you can also start, this is also freely available. So the square attack, so this square cipher was actually an ancestor of the AES. So somewhat similar kind of ideas exist there also, okay. So the designers themselves gave these attacks, and therefore the name square attack actually. This was originally proposed for square, but it works for AES as well, okay. So next day's topic we will discuss. So you see that it is quite difficult to design a block cipher, okay. So it's not so easy to make it secure, and the central idea is on the S boxes. So we will again concentrate on the overview on S box design principles and discuss on them.